Now let's learn how to solve Diophantine equations. What are Diophantine equations? These equations are nothing but a polynomial in two or more variable, uh, such as say 3a square plus 4b cube equals to 7. Okay, this is what a Diophantine equation is called. And here we want to find the values of a and b which satisfy this equation, but the condition here is we are only interested is in integral solution, which means a and b has to belong to the set Z. We are not interested in real solution or say rational solution, like if say a equals to 1 by 2, b equals to 1 by 3 satisfy this equation. They may very well satisfy this equation, but we are not interested in these solutions. We are only interested in integer solutions. Nor are we interested in irrational solutions, nor are we interested in complex solutions. Okay, we are only interested in integral solutions. So let's see how to to solve these equations. You can clearly read here, this is Diophantine equations. We are supposed to find all integers ab such that ab satisfy this equation. In this problem we are supposed to find all integers a, b, c, d such that these integers satisfy all these three equations simultaneously. Okay, and what are the methods or techniques we use to solve these equations? Well, there are many methods, techniques. Today we'll only be looking at these two. How parity and factor method technique, you won't find a method as such written in books or anywhere else. This is just my terminology. Okay, so these three problems we'll be solving through using these two techniques. And what are these techniques? Okay. What is parity? First let's discuss what is parity. Parity is nothing but the property of a number, whether it is even or odd. So let's say mm, mm, we write some equation. Let's take 2a cube equals to 4b cube plus 7. Say this equation. So the parity of left hand side is even. This left hand side 2 divides left hand side, so it is even, and this right hand side, since this is even and this is odd, so their sum will be odd, so this is odd. Right hand side is coming out to be odd, so these equations will never have a solution because an even number can never be equal to an odd number. So this is what parity is. Both left hand side and right hand side have to have same parity. That means both have to be even or both have to be odd. Okay, now let's see what are factors. Here also, if suppose a number say 5 divides left hand side, then 5 also has to divide right hand side. Say in any equation, in this equation, since 4 divides right hand side, 4 is a factor of, left hand side, 4 is a factor of left hand side, therefore 4 has to be a factor 4 also has to be a factor of right hand side. Okay, so now that you know these two facts, using these two facts you can more or less solve all of these problems. So let's go one by one and solve these problems. First one says, if a square plus b square equals to c square and c equals to b plus c, then prove that 4 divides b. Okay, let's write it here, and c equals to b plus 1. Since we have to prove 4 divides b, so let's eliminate c from this equation. As we don't care about c, then we can also eliminate c. C is b plus 1, so c can be written as b plus 1. Let's simplify this. We'll get here b square plus 1 plus 2b. we will cancel out b square by b square, and here it comes out to be a square equals to 2b plus 1. Okay, now you can very easily see that this right hand side is odd, as it is of the form 2n or b plus 1. This is even, this is odd, so their sum will be odd. So right hand side is odd, which implies left hand side also has to be odd. So this gives us the information that we got is a is odd. Okay, this information we have now. Okay, now since a is odd and a square of an odd number is of the form 8k plus 1, this we have learned in our very first video. If a is an odd number, then its square, a square, will be of the form 8k plus 1 for some k belonging to integer, of course. Okay, so in place of a square we can write 8k plus 1 equals to 2b plus 1. Let's cancel out 1 from 1. We get 8k equals to 2b. Then we can cancel out 2 from each side. We get b equals to 4k. Now since 4 divides right hand side, 4 has to also divide left hand sides. So from this we get 4 divides b. This completes our solution. Okay, so our first problem is solved. Let's move to question number 2. This says, question 2 says, we have to find all integers ab such that this equation ab satisfies these equations. So let's write it down here. Okay, similarly 4 divides left hand side, so 4 also has to divide right hand side, that is right, and left hand side is even, so this whole thing also has to be even. Okay, we observe this is odd, so for this side to be even, this term have to be odd. Okay, so from here we got 7b square is odd. This implies b has to be odd, because if b is even, this term will become even, so b have to be odd. Okay, now again, since b is odd, b square can be written as 8k plus 1 for some k integer k. Okay, so let's replace this in our equation. Okay, so let's write it here again. 4a cube equals to 7. In place of b square we write 8k plus 1 plus 3. So from here we get 7 into 8 into 8k plus 7 plus 3. We get 8 7 is 56k plus 11. So we got 4a cube is this. Now we have to find integers a and k such that these two satisfy this equation. So from here we can see 4 divides left hand side, so 4 also have to divide right hand side. So from here we get 4 divides 56k plus 11. So 4 divides this 56, so 4 also have to divide 11, since 4 divides this whole term. So from here we get 4 divides 11, which is absurd. This is not true, so this never happens. So there is no solutions to this equation. Since after calculation we have come to the conclusion that for this equation to have solution, 4 has to divide 11. 4 never divides 11. Not never, it doesn't. Not in some case it can divide. 4 doesn't divide 11. So for that reason this equation cannot have any solution. So no solution is our answer. There are no integers a and b such that when we put them back into this equation is satisfied. Okay, so we have solved our second problem. Now let's move to our third problem. Okay, this says find integers such that all these three equations are satisfied simultaneously, which is to say that we have to find an integer d such that 2d plus 1 is square. For some integer d, 2d minus 1 is also a square, and for the same integer d, 5d minus 1 also have to be a square, and for the same d, 13d minus 1 also have to be square. Okay, I can think of d equals to 2. So this will give us 5 into 2 minus 1, which is 9. This is a square. But will d equals to 2 also work here? D equals to 2 to 4 minus 1. 3 is not a perfect square. So d equals to 2 doesn't work. Okay, so instead of using hit and try, let's solve this problem properly. Okay. From here, what can we do? First, let's take this one on the right hand side. So let's write this equation again in this form. 2d is equals to a square plus 1. 5d is equals to b square plus 1. 13d is to c square plus 1. Okay. From now, we see this left hand side is even. So this term also have to be even. But this is odd. Now for this term to be even, this has to be also be odd. So from here we get a is odd. Now that same technique again, since a is odd, so its square will be of the form 8k plus 1. So we can write this equation. We can write this as 2d equals to 8k plus 1 plus 1. So d is 4k plus 1. Okay, what can we say from here? We clearly see this is odd, so d is odd. Yes, d is odd. So now what we have is a is odd and d is also odd. So let's write it here. A is odd and d is also odd. Okay. Now since d is odd, this whole term is odd. Now this also have to be odd. This is already odd. So this have to be even for this whole term to be odd. So from here we get b is even. You see what we are doing here? We are trying to find out the parity of each number, whether it's even or it's odd. Since till now we can see a is odd, d is odd, b is even, and what can we say about c? D is odd, so this term is odd, so this whole term is odd. It can only be odd when c is even, so c is even. So now we have parity for each of our variables a, b, c, d. We know the parity of each of them. Okay, so now what do we do? Now what we'll do is, first let's name these equations. Say it is 1, 2, 3. Okay, what now we'll do is we'll subtract 2 from 3. So 3 minus 2. What we'll get from this? We'll get AD is equals to c square minus b square. Now since b and c both are even, so from here we can say b can be written as 2l1. Just a second. 2l1 for some integer l1, of course, and c can also be written as 2l2 for some other integer l2. So let's replace them here. It will become 2l2 power whole square minus 2l1 power whole square, which in turn becomes 4l2 square minus l1 square. 8D. From here we get 2D is equals to L2 minus L1 multiplied by L2 plus L1. Okay. Now here we know that D is odd. Okay. So we know D is odd. Now say let's see what the parity of L2 and L1 can be now. Can they have opposite parity? Say L1 is even, L2 is odd. So odd minus even, odd. Odd plus even, odd. So odd multiplied by odd, it will be odd. And this side is even because 2 is here. So even equals to odd. This cannot be true. So their opposite cannot be, no, parity cannot be opposite. We'll get the same result if we take L2 is even and L1 is odd. We'll get the same thing. So the only possibility is for them to have same parity, which is that is both can be even or both can be odd. Okay, so say both are even. Doesn't matter what we take, even or odd, we'll get the same result. So say let's say both are even first. So even minus even, even plus even, even. Now let's say both are odd, odd minus odd, we'll get again even. Odd plus odd will again get even. Even multiplied by even is even. Even multiplied by even is even. In both these cases, we are getting both these brackets are even. Doesn't matter what parity of L1 and L2 we take. If L1 is odd, L2 is odd, we get the same result. And if both of them are even, we get the same result again. So from this, we know that these two brackets are always going to be even. This is going to be even and this term is also going to be even. So these can be written as, since L2 minus L1 is even, we can write L2 minus L1 as 2O, say S1, and L2 plus L1 we can write 2S2. So write it here, 2S1 multiplied by 2S2, get 4 multiplied by S1 S2, and here we have 2D. From here we get D is equal to 2S1 S2. So do we know right hand side is coming out to be even since 2 is here, and we know D is odd. So odd equals to even. This can never be true again. So this, there is no such D that will satisfy this equation. So this equation 2 also have no solution. As we have made our whole calculation that for this equation to have a solution, A has to be odd, which implied D has to be odd, which then implies B and C both have to be even. And from then on, we then calculated this calculation, which then gives us this absurd thing. So it is essentially saying for that equation to have a solution, this has to be true, but this is never true. So that equation will not have any solutions. Okay, well, as it turns out, both of our questions, second and third, had no solution. This doesn't always happen. Many or mostly Diophantine equations have solutions. It just so happens that these two equations had no solution. We'll see in next or future videos Diophantine equations which will have solutions. Here, these two equations had no solution.